Have you ever watched a candle burn until the wax disappears or noticed how iron rusts over time? No matter how hard we try to stop it, these transformations are not just coincidences, they're guided by invisible rules of nature. Today, we are going to uncover one of the most fascinating concepts that governs whether a reaction happens or not: Gibbs free energy. By the end of this video, you'll understand exactly why some changes are spontaneous and others need a little push. Think about this for a moment. Just because something releases heat doesn't automatically mean it will happen on its own. Sometimes, reactions absorb heat and still proceed naturally. Confusing, right? This is where Gibbs energy steps in as a master predictor. It blends two essential ideas: enthalpy, which measures heat content, and entropy, which measures disorder. Together, they create a powerful tool to determine the fate of any chemical process. Let's look closely at how Gibbs energy is defined. The formula is G equals H minus T times S, spelled out. That's capital G equals capital H, enthalpy, minus capital T, temperature, multiplied by capital S, entropy. When we talk about the change during a reaction, we write delta G equals delta H minus T times delta S. Remember, delta G tells us how much energy is available to do useful work. Delta H shows how much heat is released or absorbed. And delta S reveals how much randomness is created. This simple equation captures the push and pull between order and energy. So, how do we actually use delta G to predict if a reaction will happen? Here's the golden rule: if delta G is negative, the reaction is spontaneous, it goes forward by itself. If delta G is positive, it's non-spontaneous, you need to supply energy. And if delta G equals 0, the system is at equilibrium, no net change occurs. Imagine rust forming on iron. Its delta G is negative, so the process continues naturally. But if you want to split water into hydrogen and oxygen, you'll need to add energy because delta G is positive. It's like nature's scoreboard for chemical reactions. Gibbs energy also reveals how far a reaction will proceed before stopping. At equilibrium, delta G becomes 0. There's a direct link between Gibbs energy and the equilibrium constant, K. The formula goes like this: delta G standard equals minus R times T times the natural logarithm of K. Delta G equals minus R, the gas constant, multiplied by T, the temperature in Kelvin, multiplied by L in K. When K is large, meaning more products are formed, delta G is negative. When K is small, favoring reactants, delta G is positive. This equation is a bridge connecting energy changes and chemical balance. Let's walk step by step through an example to make this crystal clear. Problem: calculate the equilibrium constant, K, at 298 Kelvin if the standard Gibbs energy change is minus 13.6 kilojoules per mole. Step 1. Recall the formula. Delta G standard equals minus R times T times L in K. Step 2. Insert the values. Delta G is minus 13,600 joules per mole. R is 8.314 joules per mole per Kelvin. T is 298 Kelvin. Step 3. Calculate the product of R and T. 8.314 times 298 equals 2,478. Step 4. Divide delta G by negative 2,478 minus 13,600 divided by minus 2,478 equals 5.486. Step 5. Find the analog to get K. K equals e raised to 5.486, which is about 241. Answer: the equilibrium constant is approximately 241. Simple, isn't it? Gibbs free energy is everywhere in your daily life. It tells us why fuel burns to release energy. It explains why batteries power our devices. And it shows how our bodies convert food into movement. Just remember this core equation: delta G equals delta H minus T times delta S. It's the ultimate predictor, combining heat, randomness, and temperature to decide whether a reaction will go forward or stay still. Next time you see rust, a burning candle, or even a melting ice cube, you'll know Gibbs energy is working behind the scenes. Stay curious and keep exploring the science that powers our world.